All right. So in this section, we're going to look at and kind of do the same thing we did in 6.5, where we were looking at averages of averages and how that, if you look at all the possible averages of samples, you would get a normal distribution of that. Now we're looking at probabilities of things occurring, binomial experiments, success, failure, and we're going to use kind of the same setup for the most part. Now, most of this is just going to be looking at a normal binomial experiment and trying to approximate it into a normal curve. I shouldn't say a normal binomial experiment, a typical binomial experiment, and try to approximate it into a normal curve. And then at the end, we'll talk a little bit about averaging, a bunch of samples of possible things to see if, we could use that as well, like we did the average of the average. But that's just going to be a real short thing at the end. Most of this is going to be a binomial experiment that we are trying to normalize there. Okay, so a reminder what a binomial experiment is. You got two possible outcomes, success, failure. Again, success doesn't mean good. Failure doesn't necessarily mean bad. It just means how you're defining the probabilities. If you say a business, closing, there's a certain percent that happens, that might be considered a success, whereas the business staying open might be considered a failure, depending on how you set the percentages. So, or the proportion, probability. So, be careful about those words, success and failure. They don't mean good, bad. That's not what they mean. They just mean how we're defining the probabilities. All right. Also, the probability from one trial to another can't change. And that's when that means it's independent. So from one thing to another doesn't change. So if you think about like those problems you might have talked about earlier, where you draw a ball out of an urn and you don't put it back in, well, that would not be a binomial experiment because it changes if you don't put it back in. Now, if you take one out and say, is it blue? Yes or no? And then you put it back in and mix it up, then yes, that could be a binomial experiment. But if you don't put it back in, that's a different type of experiment, and that's not what this is talking about. All right, moving on. Maybe moving on. Come on. All right, there we go. So again, we're going to define some symbols here we're going to use so we know what we're talking about. Lowercase p is the probability of success for one trial. Lowercase q, it equals to 1 minus p. It's a complement, and that is the probability of failure. So if there's a 20% chance of success, there's an 80% chance of failure. So 0.20 and 0.80. So those always add up to be 1, those two probabilities. N, number of trials. How many trials are we taking? R, number of successes we get or we want to get. N times P. So how many trials times the probability of success is going to give you the mean. And this is how many expected successes you would think to get. So, again, let's say the probability of success is 0.20 and you take 100 trials. Well, you would expect to get 20 successes out of 100 trials with a probability of success of 0.2. Now, does that mean you will get that? No, but that's where it should kind of, like, if I took a sample of 100, it should be around 20. It should be, 20 should be where the middle is. And sometimes it'll be a little lower or higher, kind of off to the one of the sides. Probably not likely to be very extreme one way or the other, but right around there. And then the standard deviation, the way we calculate that, again, square root of the sample size times the probability of success times the probability of failure. You multiply all that together. And again, all this comes from when we talked about binomial experiments in an earlier section. So go through, you go through your notes or book or whatever back in that section if you need more refreshing on what these things are. But these are going to be symbols we're going to be using. All right. Now, in order for this to be approximately normal, we have to guarantee a certain size. And that size means we have to expect more than 5 successes and more than 5 failures, both. So, the minimum it would be size like 11. That's the smallest possible group you could get, would be size 11. But you kind of have to look at what the probabilities are and figure it out. So if you take, again, your expected mean, remember that's the average. How many do you expect? How many successes do you expect? You multiply those together, greater than 5. How many failures do you expect would be the number of trials you have times the failure rate, probability of failure. Multiply those have to be bigger than 5. Now you might wonder, why don't they just say, if it's bigger than 5, why don't they just say 6 or bigger? Well, remember, this doesn't actually have to be a value you can get. It's the mean, it's the average. So it doesn't actually have to be one of the actual values. So you could get like 5.1, and that would satisfy this condition. So it just has to be bigger than 5. It doesn't have to be 6. It just 5.1, 5.7, something like that would be fine for both of these. The larger the number of trials, the better the approximation is. And again, this is what you should feel like when you leave this course in a year from now, and someone says something about statistics. This is one thing I hope that you never forget, is the more you take in, the more information you take in, the better your approximation is going to be. It's always better to take more information than less. All right. In order to most closely approximate a normal distribution, we're going to have to do a continuity correction. And so what's going on here? Let me see if I can explain it. So let me turn on my little pad here. Hopefully it'll talk to the computer. All right, there we go. All right. So think about if I were to draw a graph here, it's going to be a histogram, because you have like 1 success, you got 2 successes, and so on. All right, 3. And so if I want to say, let's say I want to be less than 3, well, remember 3 is kind of the middle of this curve, this histogram chart. So what would I want to do is less than 3. I'd actually want to go up here to 3.5 and go everything less. So I get this entire bar counted, not just half of that bar. I would want the whole thing. So I'd push it up to the edge of that category for that number. And the same thing, down, I'd get all these bars down here. So we're going to do a little bit of adjustment. So what's going to be tricky is you're going to start with so many successes you want to get, and then you're going to adjust it slightly one way or the other and get so many values you want to get. And then we're going to say, oh, let's convert it to our standard curve, our standard normal distribution, and we're going to convert it to z. So this is going to often, pretty much all these problems are going to involve at least 2 conversions, maybe more, but at least 2. Switch it between 3 different values. All right, so let's take an example here. Let's say I want to go less than or equal to 15. I want number of successes to be 15 or smaller. And so what I'm going to do is I'm going to adjust it a little bit, and it always go bigger. You always go bigger. I want 15 or smaller. So, and I shouldn't say bigger. I should say a larger area that we're investigating. So I'm going to go a larger area. So think about, like, if I'm doing, let's see where we at. I should really set this up to go the other way. Okay, so from here down, right? And so I'm going to adjust this a little bit higher, so it's the space is a little bit more area involved. You're always going to do it that way. You're always going to adjust it so you get a little bit more area involved. And then, so if you're going down, you always push it up a little bit. And likewise, if you're going up, you're always going to push it down a little bit. So again, same idea is like, you're at a certain spot, and I want to go here. Well, I'm going to adjust this a little bit so I get a bigger area involved. So you're always going to adjust this so you get a little bit bigger area. What if I want to go between 7 and 20? Well, again, think about, I want to make that area a little bit bigger. I'm going to push both ends outward a little bit. So the 7 is going to go to 6.5, and the 20 is going to go to 20.5. So 6.5 to 20.5. So you're always going to adjust the area slightly bigger. You're always going to adjust the area slightly bigger so that this does a better approximation of the normal distribution. All right. Less than 47. So this is where I said, usually you'll do like 2 switches. This you might do 3 switches. Less than 47 means I actually want to get 46 or smaller. That's how I should interpret it. Because with number of successes, you either get a success or you don't get a success. You don't get like half a success. So if it says I want to get less than 47 successes, that means I want to get 46 or smaller successes. Again, now I want to adjust the area slightly. So I'm going to push that up to 46.5. And notice that's part of the reason why we're changing letters here is R is successes. And you either have a success or you don't. But X doesn't have to be successes. X is just a value. And so that's why we switched the letter here is to say, okay, I can't get 46.5 successes, but I'm looking for a value of 46.5. So that's why we can do that. We switch that letter. If you're wondering, why are we bothering to switch the letter? That's why. That's why, because we're not anymore saying successes, we're just saying values. And if I want to say greater than 25, again, greater than 25 would mean 26 or higher. 26 or higher, and then I would adjust that area, and again, I would push the area outward, so it would be 25.5. Since I'm going up, I need to nudge it down a little bit, so I get 25.5. What if I want to go between 25 and 47? So again, that really means I want to get 26 to 46, right? That's really what it's saying. I want to get 26 to 46, including both ends. And then once I have it set with those, I'm going to nudge them both ends back out. So it's going to go to 25.5 and 46.5. I'm going to nudge both ends out. Okay. So if you're not sure about this, please go through these examples again a couple times till you feel confident you can do this. Because this is what you're going to have to do this like a lot on these problems. Every problem you're going to have to do one of these adjustments on. Okay, let's look at page 341, number 12. 341, number 12. All right, what are the chances that a person who is murdered actually knew the murderer? And it goes through, and they say, by talking to family and doing investigative work, they find out that the probability that a victim knew who murdered them is 0.64. That's the probability that would happen. All right. Chances murdered. Suppose that you had a detective and they had 63 unsolved murders and they were investigating, So what is the probability that at least 35 of the victims knew their murderer? Okay, so before we even get started, we need to make sure this situation can be approximated to normal. And what that means is n times p has to be bigger than 5, and n times q has to be bigger than 5. So let me go ahead and figure out what q is. Q, remember, is 1 minus 0.64. So that's going to be 0.36. That's what Q is. And I'm going to use Q for a lot of this stuff. So I might as well go ahead and calculate it. Let me go ahead and calculate the mean, right? That's the mean is n times p. So let me go ahead and calculate that. 63 times 0.64. That gives me 63 times 0.64. 40.32. So that's something I got to know. And on top of that, it's bigger than 5, right? That's NP. NP has to be bigger than 5. So that's good. I also know NQ is bigger than 5. How? I didn't calculate it. How do I know? Well, 63 is all of them. And if I'm just a second. Okay, sorry for the interruption here. You didn't notice, but I did. So what was I saying? I was saying I know the number of predicted failures is more than 5. How did I know that? Well, 63 is how many success or failures I should get. Well, if I got 40 predicted successes, then 63 minus 40.32, 63 minus 40.32 is 22.68. That's the number of predicted failures I would have. So both check out. So you really only have to calculate one and then just take that away from the total, and that will tell you the predicted number of the other side. But you can calculate it. You could say 63 times 0.36, and again, 22.68, same number. So you can work it out if you need to, but you don't need to if you do one of them. Let me go ahead and do the standard deviation. So I know this is that number. And the standard deviation, again, is successes, probability of, trials, probability of success times probability of failure. So sigma is going to be approximately 63 times 0.64 times 0.36 square root. It's about 3.81. We'll say 3.81. So I'm going to use those values in the problem along with these other numbers. So I might want to just kind of keep a note of them so I can find them. Right. All right. So let's get back to A. A, at least 35 of the victims knew their murder. So let's see what that's talking about. So again, P, capital P is for probability, and lowercase p is the probability of success. So don't get those, this is case sensitive. Be careful about those. Don't make them the same. Otherwise, it's going to get confusing more than it is. So probability that at least 35, so that means greater than or equal to 35 of them knew their murderers. So what we're going to do, again, this is already an equal to, so we're going to nudge it out. We're going to nudge it out, make it a little bit bigger. So we're going to say, what's the probability that X is greater than or equal to 34.5? We're going to go a little bit lower in this case, since we were looking for up, and we're going to go a little bit lower to get a wider area to better approximate this. Now, in order to figure this out, I have to turn it into the normal distribution. So remember, you're going to go from, oh my goodness, I messed this up. This should be R. Shame on me. That's not R. This should be R. So remember, I'm going to go from R to X to Z. So I need to convert this to Z. So my Z is going to be the value minus the mean. So that's why I said I need to note what that is, 40.32, divided by how big a standard deviation. So how many standard deviations would this be? 34.5 minus 40.32, divide that by 3.81, and that would be negative 1.53. Again, we're going to go to 2 decimal places with our standard deviations, with our z-scores, because that's what it is on the table. So converting this into z-scores, this is going to be, what's the probability that z is greater than or equal to negative 1.53? And then we have another issue, because our table isn't set up to go greater than, it's going to have to go less than. So we're going to do 1 minus the probability that z is less than or equal to negative 1.53. Do the complement. So 1 minus, and I'm going to look at my table here, negative 1.53. Looks like 0.0630. So 1 minus 0.0630. There is a probability, a 9.937 probability that at least 35 of them knew who killed them or aware of the killer. All right, so let's look at B. At most, 48 of the victims knew their murderer. So, very similar probability that R is less than, at most, would include 48, less than or equal to 48. And again, we're going to bump that out a little bit. And we're going to say less than or equal to 48.5. We're going to, again, push it up a little bit. So we get more area, just to have a better approximation for this, because it has those histograms. And then we're going to go to the Z value. So change it to the X with the adjustment, and then we're going to go to the Z. Z equals 48.5 minus 40.32 over 3.81. Throw that in our calculator. Let's see what we get. 48.5, 48.32. Divide that by 3.81. And that's going to give us 2.15 about. And so what's the probability that Z is less than or equal to 2.15 standard deviations? And great, that's how our chart's set up to go down. So we'll just look at the positive side chart, and 2.15 looks like 0.9842. That's what it looks like. All right. Make sure I'm right on track. 0.9370. Oh, I should put a 0 there. Yeah. And then 0.9842. Yep, we're looking good. And things are about to get tricky. Let's see. Yes, I did put another slide in there. Okay, so I added another slide here just so that we could do the next ones without cramming them in there. So again, this is all the information we already calculated. Samples, probability of success, probability of failure, our mean, our standard deviation. And so now we're going to C. And C and D are tricky. So let's watch. Fewer than 30 victims did not know their murderers. Well, notice the probabilities we were given were based on they did know their murderer. So they're flip-flopping it on you. Now you could go back and recalculate the mean based on 0.36, and you could call 0.36. I'm not going to do that. I'm going to I don't want to change gears halfway through the problem. Instead, I'm just going to try to convert what they're telling me into that they did know. All right, so fewer than 30 did not know. So I'm going to say 63 minus 30, 33, fewer than 3. So I'm going to say 33 or more did know is how I'm going to interpret that. What's the probability that 33 or more did know? If 30 or less, fewer than 30, well, okay, hold on. See, now I'm messing myself up. Fewer than 30. That means 29. I should have done 29 here. See how they get it's so tricky. It's so tricky. So this should be 34. Okay, all right. We're gonna get that. 34. Fewer than 30. So that meant 29 or less. 29 or less, which means 34 or more did know. Now I'm going to convert that to my x's. So again, I'm going to bump the area a little bit, 33.5. And then I'm going to figure out my z value, 33.5 minus 40.32 over 3.810. So that is about 33.5 minus 40.32. Divide that by, okay, negative 1.79 and higher. So what's the probability z is greater than or equal to negative 1.79? Again, that's not how our table is set up. So we're going to do 1 minus the probability z is less than or equal to negative 1.79, the complement. And so from negative 1.79 down, 0.0367. So 1 minus 0.0367, 0.9633. So the probability that fewer than 30 did not know their murderers was 0.9633. Yep, that looks correct. All right, so we're on the right track. So see, that almost messed me up. Watch out. These are tricky. You got to kind of really decipher what they're saying. More than 20 did not know. More than 20. So if more than 20 did not know, that means 21 or more did not know. So 63 minus 21, so 42. So what's the probability? So 21 or more did know. That means what's the probability that 42 or less, 21 or more did not know. So 42 or more or less did know. Let's figure out that probability. So again, we're going to do our adjustment. We're going to go in less, so we're going to bump the upper edge up a little bit, 42.5. We're going to convert that to a z value, 42.5 minus 40.32, 3.810. Throw that in there, 42.5. Looks like about 0.57. So what's the probability z is less than or equal to 0.57? And great, that's how our table's set up, 0.057. Looks like 0.7157 is that probability. Yep, and there we go. So watch out on these problems. You might be doing like, I got it. I did this problem twice. This is the second time I've done this problem, because I made, some mistakes. Like I almost made this mistake. The first time I made it, I didn't notice that they had said, what's the chance that they on C and D that they did not know? And so I was doing it again for that they did. And you got to do that switch. You got to watch out for it. So be careful about those. All right, let me have you pause this. Try to do 1, 3, 5, 7, and 11. And again, watch out, read those questions very carefully, read the directions very carefully, and pause the video, do those problems, and then come back. Okay, all right, so we're back. Now we're going to talk about approximating this proportion using trials. So I'm going to go there. Let's see. Right. Okay, so taking many different experiments of n trials and determining their approximate proportion of success. The way you figure out the proportion is you say, how many successes did I get divided by how many trials? And that'll give you the proportion of success. So like if I do 40 trials and I get 8 successes, 8 divided by 40, 0.2. That's my that looks like my probability of success. Now that's a sample statistic because I use a sample to figure it out. But I do another one, I do another one, I have to do another one. And so again, I have to make sure these are large enough that I'm getting more than 5 successes, more than 5 failures on these. But as long as they're large enough, I can approximate the averages here to be normal, these proportions to be normal. So the average of all these values should be, if it's done correctly, and I could look at every single size n trial and calculate its proportion, that average proportion. So I'd calculate proportion. This one came out to be 0.2, another one comes out to be 0.19, another one comes out to be 0.21, and if I average all those out, I get the true proportion. That's what this is saying, is the average of all the sample proportions should be equal to the true proportion. The standard error, again, the standard error is a little bit different than the standard deviation. It's based on it. But with this way of calculating, this is how you'd calculate. You'd say, this is what I predict the population standard deviate, or let me check. The population probability of success times the population probability of failure divided by the sample size, and then take the square root of that. And that would be the standard error. That would be the standard error. All right. So let's look at number 20 here. Number 20. Okay, suppose we have a binomial experiment in which success is defined to be a particular quality or attribute that interests us. Suppose n equals 33, the probability of success is 0.21. Can we approximate the p-hat distribution by a normal y? What's the values of mu? And okay, so for A, it asks us, and what we need to do is, again, we need to take n times p. How many successes are we looking at? 33 times 0.21. So I got 6.93 That's bigger than 5. Great. And the other one has to be also, again, you could do 33 minus 33 minus 6.93, or you could do 33 times 0.79. 79 Q is 0.79, right? Probability of failure. But it would work. You could work that out. 33 minus 6.93. So you should get for failures, predicted failures, that's also bigger than 5. So yes. So yes, this can it, yes, can be approximated by a normal distribution. Okay. And then it asks us, go ahead and calculate the average of your sample proportions. Well, again, that's going to be equal to P. So that is 0.21. So even though it says calculate, it's just identify it. Now, it also asks us to calculate the standard error of that. And so remember, that is probability of success, probability of failure over the sample size, take the square root of that. So square root of 0.21 times 0.79 divide by a sample size of 33 in this case. So 0.21 times 0.79. And it looks like the standard error is about 0.07, I don't know, I'll say 71. Yeah, we'll just go that far. Okay. And then for B, suppose n equals 25 and p equals 0.15. Can we safely approximate p to, by a normal distribution? So again, we need to do n times p. So this time it's going to be 25 times 0.15. So 25 times 0.15. And I got 3.75, which is less than 5. So no, the sample size is too small. Too small. Now, I'm saying the sample size is too small for this p-value. If I had a higher p-value, I probably could use a sample size of 25. So it's not that 25 itself is too small. It's that 25 times the probability of success is too small. So for this particular situation, it's too small. But in other situations, it might not be. All right, suppose n equals 48 and p equals 0.5. Can we approximate this to a normal? Why? What are the values of that? Okay, so a little, obviously it's going to be big enough because they're asking us to calculate those other values, but we're going to go through the steps. So again, n times p, 48 times 0.15. So this is the same proportion, but we're using a larger sample. And this time we got 7.2, which is bigger than 5. That's our predicted number of successes is 7.2. And again, if you took 48 minus 7.2, you would get 40.8, which is again bigger than 5. You got to check both the failures and successes. Make sure both of those come out to be bigger than 5. But obviously, if this number of successes don't make it, it doesn't matter what happens with the failures. But if the successes make it, you also have to check the failures, and the failures would still make it. Can we approximate this? Yes. Yes. It can be approximated. Both n times p and n times q were more than 5. That's why. Its sample size was large enough. All right, and then again, we're going to calculate the average of our proportions. And again, that should just be what p is, so 0.15. And then we're going to calculate our standard error of the sample proportions. And that's going to be 0.15 probability of success times 0.85 probability of failure, all divided by 48, our sample size, take the square root. 0.15 times 0.5, 48. So it looks like that is 0.005. Yeah, 0.005. Oh, no, sorry. I can't read my own calculator. Let's try that again. 0.052. 0.052, sorry. All right, there we go. So that's how you calculate that. Okay, then I'd like you to do 17 and 21. And that completes chapter 6. And we will be having a test shortly on chapter 6.